Good morning, everybody, and welcome to our SPHN webinar. In view of the many further and new developments, but also taking into account the many new data providers and stakeholders and key players for data-driven biomedical research projects in Switzerland, we will today give you an update on the SPHN Semantic Interoperability Framework and its Toolstack. Most of you probably already know the Swiss Personalized Health Network has developed a national framework and comprehensive tool stack for the semantic representation of health data in a knowledge graph using Semantic Web technology. And since already a while now, this framework has been implemented in all the 5 Swiss university hospitals to facilitate the sharing and integration of various different types of health-related data from different sources. The interoperability goals of SPHN are primarily to advance medical research through the availability of health data prepared in accordance to the FAIR principles. You will hear a lot about the FAIR principles in a minute, but also to advance Switzerland with regards to the once only principle for health data, right? So we have that once only principle already in many other domains, but we do not have it comprehensively in the health data field. But also one important goal is ultimately to allow hospitals to make interoperable health data available in a cost and time efficient manner. And this is why we do all this, why we put so much effort in our interoperability framework strategy, of course, with the great help of all our 5 university hospitals, but also other experts in the field. Our speaker today is Dr. Sabine Österle. Sabine is our team lead data interoperability here in the Personalized Health Informatics group at SIB, Swiss Institute of Bioinformatics. And she's responsible for all of the central components and the strategy development of the SPHN interoperability framework. And with this, I would like to give Sabine the word, and I look forward to your presentation, Sabine.
Thanks a lot, Katrin, for the nice introduction. And thanks a lot for all of you for joining, even though on such a warm day. So without further ado, I would like to jump directly into the topic. But before I talk about SPHN, I would like to do a bit of a recap about how we use data in research, or especially in healthcare research. And I think when we think about the past of data, then quite often we say, oh, we have that new study, I have that new idea, I think about which data do I need. I collect that data prospectively, I publish my paper, and then a bit, as you can see on that picture, like with the one-way PET bottles, actually it's thrown away, or it's actually put somewhere, but actually not many people are using it because the data was really tailored to that one use case, and the kind of question is normally analyzed. When we think about the present, or I think all of these stages are also a bit intertwined, is we are starting to build a lot of archives. As you can see it on that picture, we have a box which actually is described with very rich metadata so that we know what is in the box. But then do we really know what is in the box? Because normally we are not just interested to know, oh, there is a data set about diabetic patients which also get a certain medication, but we really also want to know a bit the insights. So how many of that patients actually got that medications, and how is the kind of combinations. And also I would like to already know, can I combine that box on the top left, or the data in that box with the one on the top and on the bottom right? So actually, I would like to have like a mix and match when I'm reusing data, and also that then the kind of data goes together. And that brings us actually, we depict here the future where actually we have this data, as Katrin said, in an interoperable way, and we also really have the data interoperable and semantically described, and we actually know when we talk about heart rate, everyone is talking about the same thing, and we also know that. And again, I think I can say here that this is not the future anymore, but actually with SPHN, we are making a huge step towards that future to really enable that, so that we can really reuse the data, and also within a project really combine data from different sources. And I think that brings us to the FAIR principles. findable, accessible, interoperable, and reusable. And I will go a bit more into the sub-principles on a later slide. But just also, I put you here this key publication, which was actually done already in 2016, and I think really which set the cornerstone for all of that work. So again, when we think about a project life cycle, so normally we have a certain kind of planning phase where we plan our study, then we have a data generation phase or a data extraction phase, then we go to the data analysis, and then we come to the secondary reuse of data. If we now think again about our three pictures in the beginning, what mostly is done in the present is that when the project is done, we start thinking about the FAIR principles. So we think about how can we attach metadata to this data set to make actually the metadata fair to deposit it in some repository. So we think about descriptive metadata and also about the conditions for the reuse. But when you think again on the picture I had on the right, so there's really the interoperable data itself, where I can also then combine certain subsets of these data sets, then actually we need to move one step further. And actually that also means we need to actually keep the FAIR principles in mind when over the whole project lifecycle, and not at the end consider it as something we need to do because actually some funding agencies or some publishers actually are requiring it. And that actually means that when we are in the planning phase, we should already think about questions like which metadata is collected, which metadata can be reused, what is the standards we can use for the data. So really that we start using controlled vocabulary and not everyone making their own value sets for the data. And all of that, and you will see that later also in my presentation, will be then somehow nailed what we call a data schema. So really, which is a description about how the data is collected. When we go to the data generation, of course, we have to do a lot of mappings. So ETL processes between the source data, which is maybe not in that standards, to the kind of standard. We will need to attach a lot of administrative metadata so that we actually also know from whom this subset comes from. And then what we have is in our case, mostly like a hospital-specific subset of the data, which is then sent to the researcher. And what is actually also the cool thing, if we already follow these processes, when the researcher then receives the different subset, actually they are already interoperable. So when you put them together into a triple store, they can be analyzed together, so they can be linked to each other. Also, by using the standards, we already make sure that we can easily link them to the external standards like SNOMED-CT or LOINC or others. And then we have actually this, what we call a combined data set. And of course, this combined data set can be now also again made available for the reuse. And you can already see why such a data set is, of course, much more valuable for the reuse than the one which I had in the other scenarios. So to quickly summarize, why should I care about FAIR? So first, on the data analysis side, FAIR helps you to understand data from different people in your consortia. So you, if the data is really properly annotated, following the same kind of standards, having the appropriate provenance and metadata, you don't need to go back to the clinician and ask, oh, how was that measured? Oh, what is the condition here? Because actually your data is rich enough that you have all of that in the graph. Also, FAIR data is machine readable. So I think we see that a lot, that people actually start to extract some data again from some public figures in some publications, or actually that the raw data is not attached to the publication. So here I think we really need to move towards that data is available in a machine readable way, because only like that we can also later ensure also reproducibility of our research. But again, not to be say, for reproducibility, there is quite a lot of additional steps then to take. But I think also here, FAIR is a very important basis to ensure also reproducibility. And also one very important point is when we're following all these principles, we can, as I said, link the data very easily. We can actually query it by a common language. And we enable knowledge exploration, but also data inference, because as you may know, all the standards are either hierarchical standards or ontologies, and you can really use that knowledge which is in the external standards seamlessly together with your data. But I will show more examples on the SPHN case later. And of course, another very important point is for the secondary reuse. Of course, if your data is fair and you deposited it in the right repositories, you will highly increase the visibility and the reuse of your data. And I think also what Katrin said before, we are more going towards that once only principle, so not actually collecting the same data in an Excel file with a study nurse for every new study. So we can really make use of the existing data. So to go a bit more into FAIR, and I wanted to talk quickly about the sub-principles, because of course you will hear a lot of these buzzwords when I talk about SPHN and how we integrate it. So I think that's why it's very important to hear at least quickly all the sub-principles. So for findability, that doesn't mean I have a free text search on my website where I can find something. The criteria for findability is that all points, all data points and all schema points have actually a unique identifier, that we have rich metadata attached to the data, that we have a link between the data and the metadata, that our metadata is searchable. For the accessibility, it means we have a common communication protocol, so a standard communication protocol, for example, for querying, for accessing. We have the data, or at least the metadata, on a long-term availability. And when we go to interoperability, which is also the main focus of my talk today, we need a common language for knowledge representation. We need controlled vocabularies and semantic standards. And I think both of them are then more or less resulting in the E3, which is that the data can be very easily linked, and that we had a link between the data. And on the reusability side, I think here we are really talking a lot about the provenance data, and of course also about the licensing for the reuse. And I put you here a training which we did, or actually which Vasundra and I did a year ago or so, on FAIR data. So if you want to really learn more about the FAIR principles, I highly recommend you to watch that video. But now, without further ado, let's dive into SPHN and how we actually bring all of that into our Swiss Personalized Health Network. So here you see a small overview about all the different partners which are involved in SPHN. And I think what this slide should show you, yes, it's a very messy slide, that there is very diverse partners and everyone has their data, different kind of data, different standards, different formats. And as I said, we want to combine that. And how do we do this? So you can really here see, for example, we have the clinical routine data. So this is the data which is collected while a visit of a patient in a hospital. So you can see here in this example, he goes through different kind of departments while his hospital stay, and there's different kind of lab or pathology measurements taken of this patient, and everything results in a different source system. So there's around 200 different source systems per hospital. And you can again imagine it's a very diverse thing. So this is already rather complex. And then of course you need to imagine on the right side, we have clinical trial data, we have registry data, patient reported outcomes, genomic data, epigenomic data, transcriptomic, omics. And actually these data we want to combine as well. And actually you can see here our poor researcher who just gets these stars and triangles, and actually, I think in the first place doesn't understand a lot as a human and also not as a machine. So if you think about that, we want to go towards AI who should really also be able to understand that data. And also this data, yeah, if it comes in different format, it's not easily linkable. And that's really why our goal is to have data which is understandable by humans and machine, and which can be easily linkable. And how do we achieve that? I think Katrin already mentioned it, and you can see it on the right. It actually at the end should form that annotated knowledge graph. And that's what brings us to the SPHN interoperability framework. So we have a very strong focus on what we call the data semantics. So really that each element which is in the data is actually described by controlled vocabulary. So for example, I mentioned a few standards here which we are using in the SPN framework, for example, ATC, SNOMED-CT, ICD-10, CHOP, UPOM, LOINC, NANDA, ICD-0, so the genome sequence ontology. So there's a lot of different standards which we can use. But again, I need what I said before, we need to make them work together and also, yeah, bring them together. And I think that's mostly done over multi-level coding. So for example, that we sometimes say, oh, in SNOMED-CT, actually heart rate means this, and in LOINC, it means this, because then we are actually also here compatible with both communities. And yeah, I think that's really the main core. And also to saying we do this for the meaning of the concept. So as I said before, in my example, the heart rate has a meaning binding. So we say heart rate in an ontology, or the corresponding ontology means also heart rate. And with that, we are actually fixing the meaning of our SPHN heart rate, which would just be something which SPHN defined and would not be interoperable or understandable outside the SPHN community. But we're also using it, of course, for the data itself or for value sets. So for example, when we go in the example of the heart rate, there is a physiological state which of the patients, and there we also have really in the data then SNOMED-CT or LOINC or other standards. And I think really it's really important to see here both aspects on the data, but also on the schema. But again, this is just then free floating elements. So you could see about then on our right picture, that would be the blue and the red bubbles. But we somehow need to connect these bubbles and have something like a language. So when you think about it, the semantics is like our words, but now we need kind of a grammar and a kind of sentence to connect them. And this is where we use the Semantic Web technology for, so actually RDF. And this is really how then out of the different kind of bubbles on the right, we actually form the kind of knowledge graph. And also to say here, to build that graph and the fact that we are using RDF for it actually also provides us with controlled vocabulary. So controlled vocabulary about what is the meaning of the connection, what is the meaning of that kind of data point. Actually, I will show you later also a slide on which kind of controlled vocabulary we are, for example, reusing of RDFS, OWL, and SCOS. So again, controlled vocabulary is not only limited to the data itself, but also really to the annotations of the schema, how your schema works together, what is the meaning of each data point. And as I said, since we are very strictly following the Semantic Web standards, we can also make use of a so-called quality control framework, which we have built, which relies on SHACLs and SPARQLs. So again, this is again known standards, and of course we can very easily use them, and I will also show you later here some examples. And yeah, this is our implementation of the FAIR principles, and I think you will see later some more details about how the different FAIR principles are addressed. So a lot of people ask us, but why are you doing a knowledge graph? Why can't you just do a relational database, or why can I not just collect my data in an Excel file as I've done it for all of my studies? And I think what we realized really working a lot with clinical routine data, it is actually about the semantic representation of the data rather than a harmonization to fit into one data model. Because we cannot change the way the data is collected on the local sites, and data will always have different granularity on the capturing. This can be, for example, in a cohort, we only know that the patient had a diabetes, yes or no. In another case, we already know, is that diabetes type 2 or is it diabetes type 1? Did it had any complications? But still, in both cases, we talk about diabetes, but one, we have more information to it, and one, we have less information to it. So again, this should be the same concept because we are talking about the same thing, one time with richer metadata and one time with less metadata. And I think this is really important to keep in mind because when we try to really enforce, like, for example, also value sets, these are the 4 values which you need to use. If this is not possible because you have 5 values and they just don't fit onto these 4 values, then you start somehow squeezing your data into a model, and that will just result in impreciseness. And that brings me also to the next point. This is the flexibility. So the knowledge graph allows us to represent very complex and interrelated data, and also this integration from multi-model sources. So again, here we can always have more connections between different data points because maybe there is some relationship between 2 data points, which we also want to express in the model. That, for example, there was a diagnosis given, and because of that, there was a certain medication given, then maybe the patient got an allergy against that. So you can really see how all of these events are really intertwined. Also scalability. So I think knowledge graphs are made for handling large data and are designed to be very scalable. Also, it's very intuitive and a visual representation. So if you think about how do you think about things? So I'm Sabine, and I'm now being here in this room, and I'm looking out of the window. So it's always like this kind of small sentences which start describing things, and that's just really the same what we model here in the knowledge graph. So another reason, as I said, is the linked data. So how that we really easily, by the IRI, so remember that is the F1 FAIR principle, can actually link when 2 things are the same because we have unique identifiers for the same things. And we also can make sure that they are then really the same and then actually melt in the graph. We can do knowledge inference with the standards and with all the publicly available resources which are out there, which follow the same principles. And as I said before, we are, with that strategy, complying with the FAIR principles. So how does this strategy look like? So we refer to it as a 3-pillar strategy. So in the first pillar, we have what we call a concept. So concepts are considered to be small semantic building blocks describing certain elements. And as with the Lego stack, with the Lego bricks, you can like combine them in different ways to form more complex concepts, which then describe different things. And I think in total, we have around 90 of these building blocks currently in the SPHN dataset. And we are, of course, working heavily on extending these kind of building blocks. And also, we are enabling the projects to reuse building blocks when they build their own concepts. So also, if a project needs to build their own concept, they never have to start from scratch. Then all of that is translated into what I said, this kind of knowledge graph, which is the common semantic representation of the data. And from there, actually, different kind of applications can be used. For example, data catalogs, for example, the different research projects, and also shared databases and platforms. And all of that is actually summarized here in this publication, which I gave you for reference down here on the bottom. When we now think about these data concepts, I would quickly like to show you one example. So this is actually from our website where we have all these concepts described. You can see here, this is a very simple concept of body side, which has actually a code, which describes actually as all descendants of the SNOMED code of body side. And it has a laterality linking to its own concept of laterality, which itself then describes, for example, if it's unilaterality left or right. And with that, we can actually describe all kind of body sites, for example, where measurements were taken, where certain procedures took place. So you can really see how this is very reusable. So quickly, again, when we talk about this use of controlled vocabulary, we have two ways of doing that. So one is what we call a meaning binding. So here you can see we have that SPHN concept of heart rate, and we actually do this meaning binding to LOINC and SNOMED CT to really have an international meaning to our concept. This is implemented via an OWL equivalent class for the more technical people here in the audience. And actually currently 64 of 78 of our SPHN concept have such a meaning binding. So you see that it's not always possible to find an equivalent meaning binding, but we really try here the best as we can to really find equivalence in that. The other way how we can use controlled vocabulary is what we call value set binding. So here you can see we have this regularity code, which has the two possible values, which is either pulse regular or pulse irregular. And these are the two kind of ways to answer it. Also, you can see here that it has this comment that descendants of these classes are not allowed. So in this case, it really means it's these two SNOMED codes which are allowed. We can also have the possibility to say all descendants of this code is allowed. So with that, you would, for example, allow a whole subset, for example, of SNOMED CT to be used in that case. And also here we have currently around 2/3 of our value sets, which actually are expressed by standards. Unfortunately, we also have a few value sets where we could not yet find an appropriate standard, so they are implemented as SPHN specific values. But we also here work very hard to actually find good and appropriate standards for representing that. But some of them are also very Swiss specific, and then it's of course hard to find international standards for doing that. Coming to pillar 2, which is actually the knowledge graph and how we are actually translating that into this formal language. Also here, I put you for a reference, a paper where we summarized all of that and really explained the rationale behind it. But in general, you can see how it looks like here on that slide. So we have here kind of an example of an administrative case. There was a patient which was involved there. He had a drug administration event, which had a drug. The drug has a substance, and you can, for example, here there was a reason to stop that giving that drug, which was actually the allergy. And of course, the allergy was against the substance, and you can see here how things come together because, of course, the drug which was given was also the drug which this patient was allergic to. So again, it's the same thing. So now this is about the kind of strategy and how we do things. But of course, how do we bring that into practice, and how do we enable our researchers who are not so familiar with semantic web technology to use all of that? And this is where our Toolstack come into play. So we have more or less 3 components in our Toolstack. So the first is the SPHN Schema Forge. So this enables you to create all these semantic artifacts in less than 5 minutes, at least from the technical side. So the idea is we came up with a process where actually all of that can be filled into an Excel file. So we have a certain Excel file where you write down your concepts, and then we provide researchers with a web service where they can upload these concepts. And out of this Excel file, we generate the RDF schema, but we also generate completely automatically the SHACL rules and the SPARQL queries for statistic and a kind of web documentation. So the screenshot you have seen before from my heart rate, this is actually part of a web documentation, which is then can be published on the web. So it's an HTML page, and this is all generated fully automatically. For that, of course, to work, what we also need is a terminology service where we provide fair and historized version of the terminologies which we are using in RDF format. And last but not least, we actually, and this will be also part of next week's seminar, that's why I'm very short on that, we also provide a tool which is called the SPHN connector, which helps data providers really to then transform their data into the knowledge graph. Let me quickly talk about the SPHN terminology service. So currently we have the following terminologies available, but we are also extending that with every release. So SNOME-CT, LOINC, ICD-10, GM, JOP, ATC, UCUM, GENO, HDNC, and sequence ontology. And we verified them and we historized some of them. And I would like to quickly talk to you about what this means and why we are doing it. And yeah, so just on the right, you now see again a publication of where we describe how we do these things, and also kind of screenshot of our Biomed IT portal, where you can see that you can actually download all these files, which you can then use in your research. So let's have a look at one external terminology. So this is the example of CHOP, which is the Swiss operation procedure. This is released as an Excel file. And the main core of that Excel file is that we have these 3 columns, which is a label, a code, a level, a code, and a label. And when you now think about it, again, looking into the FAIR principles, we said we need unique identifiers. Why do we need unique identifiers? And actually, yesterday I just said, okay, let's try to Google C1. What do I get when I Google C1? And yes, results are in German, but what I then get is C1 is a category for your driver's license. It's also a Citroën C1, which is a car. So with that, you can really see C1 in different contexts means different things. So it's actually not sufficient to have C1 as a code, but we really need unique codes. Also, what we see here in this Excel, there is no language of it. It's just, it's columns in an Excel file. A human understand what a label, a code, and a level is. But for the machine, it's just words. It doesn't mean anything. And also, yes, we as humans understand that level actually is indicating hierarchies. The computer doesn't know. It doesn't understand what a level is and why there is the 1, 2, 3, 4, 5 3. Also, metadata. There is metadata on the page where you download it, also in the file name, but also this is not machine readable. And that's actually why we actually, as I said, try to address these points as good as we can. And you can see here on the right, it's an RDF snippet out of this example, where we can see is we gave everything unique identifiers. So we created unique identifiers under our Biomed IT domain. We are also implementing, for example, hierarchies. You can see that here with the RDF subclasses. So we really have now a machine-readable way of integrating the hierarchies. We also included the metadata information, machine-readable, in the file. And with that, we are bringing these terminologies to a more fair, let's say, appearance. Coming to the next point, which is historization. So one thing is when we think about the hospitals, for example, ICD-10 coding or also ATC is really the standards which is used in the hospital since a long time. So we have actually also historic data using these standards. And when you, for example, look here on this example with ATC, what happens in these standards is, for example, that between 2016 and 17, actually there happened a code split. So meaning that the same code, this C07 FB02, actually changed its meaning between the 2016 and the 2017 version. So if you now would, as a researcher, just say, give me all codes in my historic data, you would get all the data annotated with that code, even though after 2017, it had another meaning than in 2016. Also, what is normally the case in these standards is that codes which are not valid anymore are removed from the current publications, meaning if we just validate against the newest version of that file, it will tell us that the code is wrong because it doesn't exist. And actually, we have no idea then if the code never existed. So if there's, for example, a typo, like a number switch when generating the code, or is it just an old code which is by now deprecated? And for this reason, what we did in our SPHN implementation, we keep all codes, so also codes which are deprecated, but we mark them as deprecated. And that, of course, allows us in the quality control later to distinguish between the cases where a code never existed, so is wrong, or between cases, as I said, where the code is just an old code, which is not valid according to the new version, but it was valid in an old version. And also we implemented the relationships between the codes in different versions. So for example, you can see here between 2015 and 16, we would say the code didn't change its meaning, while for 2016 to 2017, we actually would not indicate such a connection that these codes are actually the same. And of course, when you now think about you query the data, for example, you say, give me all codes with the 2023 version of this code, and actually the algorithm would go back to see until when is the code still have the same meaning, and when do I have such a breaking change, and it would only return you the result as long as that meaning is still the same. And I think this really helps us a lot to deal with the historical data which we have in the hospitals. So this is about the terminology service, as I said, which is more or less the foundation of everything. Let's quickly have a look into what is such a data concept and how would an example of that look like. So I think very fitting to the temperatures here, let's think about a patient who burned himself. So he had a burn event. So I don't know, it was maybe a fire in his house. And the kind of data which we would have is that there was this burn event. There was a certain date when this happened. There is a kind of body side, for example, the arm which the patient burned, and it was his left arm. So actually I hold my wrong arm. Also, there is a kind of degree. So how strong is the burn? For example, in my example here, it's only a first degree of burn. And then up here, I need to know which patient was affected. So this is somehow the data I would like to represent in a concept. If I now think about a concept in a more general, in a more general way, I would need to think about what is the different kind of possibilities which would be arising. For example, I can have a first degree burn as in my example, but I could also have a second or third or fourth degree burn. And what you can see here as well is I also would like to express that in a coded and an external terminology like SNOMED CT. So I looked for the 4 SNOMED codes which represent these 4 possibilities. Same here for the arm. Of course, I can more or less burn all the kind of body structures which I have. So here, actually, I would say that I need to have a descendance of body structure as a possible value to allow that I can also burn my leg or my toe or my head. And for left and right, again, this is the laterality. So here as well, we have left, right, right and left, and unilaterality to really enable to express everything what we need in our concept. And of course, thinking about that, we would need to also think about that in a more general concept-like way. So actually here, we can now see that our burn has a date time, which is directly connected to an existing date time. So this is the technical way of expressing that the format of the date time. Then the burn has a body side, which is a body side. And this body side has a code. And as you can see here, that's what we said before. This should be a descendant of the SNOMED code of body side. And our body side should have a laterality, where again, the laterality would have a code, which is the left or right. And also our burn has a severity code, which is again linked to the code concept with the 4 possibility. And actually our burn is connected to our patient, but the patient is actually represented by its pseudomized identifier. So that's why we have here the concept of the subject pseudo identifier. Also, what I would like to do for concept, I would like to add cardinalities. So I would, for example, like to say in this example, and again, this is just a random example, that for the burn, sometimes I know that which degree of burn it was, sometimes it doesn't. So I set a cardinality for 0 to 1. So I don't need to have that data element in my data, but I also want to have it at least once, or I want to have it only one time. Sorry. Same for the body side. I think I now decided if I don't know which body side was burned, then it doesn't make for me no sense on the data. So I set here a cardinality for 1 to 1. And also I necessarily need to know when it happened. And of course, that also enables you to really set the kind of connections between your different data elements. So this is now how my concept would look like. But again, this would be designing it from scratch. But actually, we have already SPHN and SPHN concepts. And I said there's a lot of building blocks which are around. And when I look into SPHN and think about what can I reuse from the SPHN data set, then I actually realize that only the things in red are the things I need, because everything else is already there. So the only thing what I need for building that concept is actually to define that new concept of burn with its different properties. I can connect it to concepts which are already existing. So all of the blue concepts are already existing. And the only thing which I actually need to specify is this special value set for my severity code. So that's also the only thing which I still need to do. But the rest can be really done by the SPHN building blocks. Now, as I said, this is a nice picture, which I hope everyone of us understood. So we are all humans. So I have done the human understandable part. But of course, I also want to have the machine readable part. And I think this really comes with the FAIR principle, the FAIR interoperability principle 1. Data use a formal, accessible, shared, and broadly applicable language for knowledge representation. So how do we get from my nice picture, which the human understands, to this knowledge representation? And this is actually where we developed Schema Forge. So Schema Forge is a web service, and also we can share the slides afterwards. So here's a link where you find this web service, the kind of template. So this is the Excel template to be used with Schema Forge, and also a very nice user guide and training material developed by Vasundra for actually using that. And you can see here, this is the web service. So it's very easy. Drop your file here and click upload. And it's really that simple. So you drag and drop your Excel into this blue box and you press run. And more or less what happens then in the background, or magically, no, maybe that's the thing. This is how our concept would look like in the Excel format. So you can see here we have the different names, a description for it, what it links to, and you can see that here is my SNOMED code. So again, very simple. Yeah, very simple for doing. And again, what happens in the background is that we translate that all to an RDF schema using RDFS and OWL. And I think I go very fast over that. So this is just all the kind of different RDFS and OWL constructs which we use to do this, to really make it this knowledge representation. This is how such an RDF snippet looks like, just for the ones of you who are familiar with RDFs. Again, you can see the same elements, for example, the severity code, the different SNOMED codes, but now actually in a computer readable form. Very quickly, we also generate quality control rules for it. So this is done with the so-called SHACL language, which is also V3C standard. And actually the kind of rules for checking the data which we generate is actually we check the validity of all classes and properties, so that you only use classes and properties in your data which were defined in the schema. So this, for example, picks up typos in concept names. It checks time frame validity, so that your start date time is not after your end date. It checks cardinality constraints, that not suddenly you connect a concept to 2 patients where you said it can only be connected to 1 patient. It checks restrictions on individuals and instances. So for example, when we said only these SNOMED codes are allowed, then actually this is checked. Restrictions on sequence paths. So again, if you specified something in your schema to be valid, this is also then checked in your data. Literal type constraints. So for example, that is when you say that something is a double or something is a string, then actually this is checked. Or if it says is a date time and suddenly you put in there a string, this will of course raise an error. And last but not least, validity of code from versioned ontology. So that's what I said before. We are actually not even giving out warnings, not even giving out errors, but also warnings and infos. For example, we inform people when they use codes which are not valid in the newest version of the terminology, but were valid in an old one. And that really also helps to for people to realize when they are using outdated codes. On the SPARQL side, again, SPARQL is the language for the queries. We also automatically generate SPARQLs for the users to do statistics. So we have one SPARQL for each concept and property to count the instances. So how often does this appear in your data? So how many patients do I have? How many procedures? How many diagnoses? It counts min-max values for everything which is a value or date time. So with that, we can really also do basic quality control. For example, if we have negative values in the lab, or if we have dates which are 200 years back, this is a good indication for also quality control lists. And last but not least, we actually, for everything which is a code, we provide a SPARQL to generate a histogram, so you can see the code distribution for these. And also we provide a SPARQL set for the conversion, so for a basic conversion into flat tables along our concepts. So again, this is all generated automatically, meaning that we don't only have that for our SPHN schema, but we have that for each project schema, which is actually designed by the researchers. And I think this is the really cool thing of generating all of that fully automatically. And I think now, due to time, I think I can quickly summarize. So actually under the hood of Schema Forge, we have 4 tools. So also all of these tools can be used alone, but again, they are also all available in this web service, which is the data set to RDF, generating the RDF, the SHACLer, generating the SHACLs, the SPARQLs for the queries, and the visualization tool for generating the HTML. Coming back to the tool stack, I think, as I said, when you are interested of how the SPHN connector works, you can dial in next week, where we have a webinar by Philipp Kraus and Katie Kalt about how then data is transformed by the hospital into the knowledge graph. So again, I will skip this part and would like to come to our take-home message, which is, when we build a fair data infrastructure, I think it's a joint work. So actually everyone has to do his or her part, and it's also not a simple task. So I think we really need everyone in the community to contribute and also to support this endeavor. I hope I could convince you that making data fair is not only helping others, but also yourself to do better research, to have more easy data linkage, they can use inference and other things. I think one other thing what we were seeing is that standards has to be integrated as early as possible into the data processing chain, especially when we want to have a sustainable infrastructure, because of course, otherwise something in the beginning, for example, at the data capture change, and actually the people doing the mapping to the standards are not aware, which proposes a large risk. And I think this is why it's very important that we bring in these standards in at the source, so as early as possible. And of course, that also brings me to my last point, that standardized data capturing using standards can then also benefit healthcare and research, while of course, when we only do it in a data processing chain for research, then actually healthcare cannot benefit from it. And that's why it's so important to do these things together at the source, so that it can actually be used for all different kind of applications. With that, I would like to come to the acknowledgement. So there is a large team behind all of that. As I said, all the hospitals and all the workforces which contributed to different parts of that strategy. And also, when we share the slides on the right, you find all the references for the different things. And with that, I think we are happy to take questions.